Hello everyone. This video outlines some common study designs in education. Now, study designs can get pretty complicated and diverse, so we're not going to be able to cover everything, but hopefully we'll be able to hit the highlights. So in quantitative research, there are four main types of study designs: descriptive, predictive, quasi-experimental, and experimental. And they're not in this pyramid by accident. They're here because they build on one another. Every predictive study has to include some description. Every experimental or quasi-experimental study assumes a predictive relationship. Experiments don't require quasi-experiments, but that will make more sense when we cover it in detail. These are the terms we're going to use, but it's worth noting that different disciplines have different terminology, and I'll try and point that out when I notice it. A quick caveat here that for most of the video, we're going to be talking about quantitative only designs, but it's important to note that mixed methods is its own type of design, and we'll talk more about that when we talk about mixed methods. Some of the things we're going to talk about today will be applicable for like the quantitative portion of mixed methods, but it's really its own thing. Okay, so back to our little pyramid. We're going to go through each of these, but the main thing distinguishing each of them is the purpose of the study, the goal. To put it super simplistically, the goal of descriptive studies is to describe things, the goal of predictive studies is to show a relationship between two or more variables, and the purpose of experiments is to determine cause. We'll explain all that more, but the main thing here is that the key distinguisher between all of these is purpose. Before we get too far with that, though, let's talk about the big split. One big split among these designs is the experimental versus non-experimental designs. The big difference here is that experimental designs, because their goal is to determine some kind of causation, include a manipulation of some kind, whereas non-experimental studies explore things as they are naturally, or if not naturally, then how they currently are. We'll talk more about what that means as we get into each one. Now, like many big divides, this one isn't actually as stark as it would seem, but we'll talk about that when we get there. For now, let's start at the bottom with non-experimental and get into descriptive studies. Okay, descriptive designs. The goal of descriptive studies is to well describe something, an experience, an opinion, the nature of a certain situation. If you're wondering what is the nature of, or how do people feel about, or whatever, that's a good indication that you're doing a descriptive study. The most common method you see in descriptive studies is survey or questionnaire designs. In fact, some people will say survey design when they mean descriptive design. Survey design actually means the creation design of surveys, not the method of administrating them. But typically, a survey is the most common of descriptive designs. And the way it works is you administer a survey to a group and then you report the results that reflect those people's thoughts and feelings. And that can be anything from here's what these people think to here's what these people experience to things like here's how many people have children in school currently. Surveys are also the most common research you see out in the wild. We've all gotten emails or prompts to fill out customer satisfaction surveys. And of course, one that you're all familiar with is course evaluations. That's a type of survey. But surveys have an obvious downside that you can only ask the perception of things, and sometimes you don't want people's perceptions. Using the example of course evaluation, there's lots of evidence that course evaluations are biased in really specific ways. In particular, women and people of color are usually rated lower by students. So if we wanted to know how well a course was going, but we didn't want to use surveys, well, then we have a couple of other options. The first is tests. If we want to know how well a course is going, one way might be to deliver a test of course content and see if the content is actually being learned. If you don't care how people feel about the course, as long as they learn the content of the course, then a test makes more sense. And we do see this pretty often in real life too. EQAO is basically a descriptive study of students in Ontario using tests as their methods. Of course, tests have their own flaws. They don't reflect everything a student knows. Students may not be able to perform on tests but still know the materials. Tests can often reflect structural inequalities that students experience. And then the second main alternative to surveys is observation. So continuing the course evaluation example, instead of surveying students, I may have a teaching expert observe and rate my class on known factors of quality. Observers, of course, can also be biased, but because they're experts typically and they don't have a stake in the course, you often get better information from that than you do from surveys, depending, of course, on what you're looking at. Of course, the flaw here is that that's also always going to be filtered through perception, and it's also expensive and difficult to do. To get detailed quantitative data, observers have to know what they're looking for, and they have to take detailed notes or carefully code recordings. And that can be things like going frame by frame to see where people are looking or how they're acting. And then, however you get those methods, once you have them, you present them using descriptive statistics. We'll talk more about what those look like in the future, but for now, the important thing is that descriptives merely describe. They don't make any judgments or inferences. So if I had course evaluations, I might say my average score was 4.2 out of 5. That's describing my score. Now I can break that down by group. Let's say questions referring to me as an instructor got an average of 4.5 out of 5, whereas questions about the course itself got a 4.0 out of 5. I can present the information broken down like that, but I can't then go on to say that I did better on questions about me as an instructor, because that's comparing the groups, and we have to do different statistical tests for that, and that makes it no longer a descriptive study. Purely descriptive studies are actually pretty rare in education. They're super common in the world at large. Election polls and census and things like that are a way of doing descriptive studies. But in education, usually we want a little more. Or if we are just describing things, we usually do a qualitative study. Okay, so back to our little pyramid. Let's move up and talk about predictive designs. Although I already talked about the big split between experimental and non-experimental, this is also a bit of a big jump in that the designs themselves suddenly get a lot more complicated. Predictive designs are all about whether there's a relationship between two or more variables. Normally, we're interested in whether two things are related. Predictive studies have the most different names also. Sometimes they're called correlational studies, sometimes they're called exploratory studies, others call them relational studies, but they're all basically the same thing. They're asking, is there a relationship between two variables? The methods here are the exact same as with descriptive, surveys, tests, and observations, and they all have the same pros and cons as they did in descriptive studies. What differs in predictive studies is you can start comparing and relating different variables to one another. Going back to our course evaluation, I could do some inferential statistics and say, yes, students rate me higher as an instructor than as a course designer. Now you may be thinking, that doesn't sound predictive. You're not predicting whether students will find you a better instructor or course designer, and that's a good point. Predictive here is used a little differently than we use it colloquially. We're not literally predicting the future. What we're doing is saying if there's a relationship between two things, then we can use one to predict the other. So if I know that my ratings as an instructor are higher than they are as a course designer, for the next course I deliver, if I only have ratings as a course designer, I can make an educated prediction that my ratings as an instructor would be higher. That's because through the previous course, I've learned what the relationship is between ratings as a course designer and ratings as a course instructor. So we call them predictive studies because they give us, the reader, the person outside of the study, the ability to make predictions in day-to-day life. Let me give another example. I did a study in which we asked university and college instructors to fill out a survey about their attitudes toward disability, and then also say how often they've encountered students with disability in their classes. We found a positive relationship. The more students with disabilities you've encountered, the more positive your attitudes towards disability. But in real life, of course, we don't know most people's attitudes towards disability. That's not a thing people, share on their Twitter profile. But if we know their encounters with disability, then maybe we can use that as a bit of a predictor. Now, you may be thinking, that sounds like a terrible idea. There are lots of things that could predict that, and that doesn't always necessarily make it true. And that's right. That's because we're doing a predictive study. You've probably heard the phrase correlation does not equal causation. And as I mentioned before, the purpose of experimental designs is determining causality. That's not the goal of predictive designs. So let's talk about that attitudes towards disability example a bit further. What we found is that there's a relationship between experience with students with disability and attitudes towards disability. Now, we can use that to make a predictive relationship, but you can't just judge people on experience. If you meet someone who is maybe new in their career and hasn't encountered students with a disability, that doesn't automatically mean they're going to have a bad attitude towards disability. And Obviously, yes, that's why it's a predictor and not a cause. We can't say it's the only predictor. We can't say that everyone with experience with students with disabilities will have a positive attitude. We can't say that encountering students with disabilities improved their attitude. In order to do that, we'd have to have some indication of change over time. We can't even say that the reverse isn't true. That is, that instructors who have positive attitudes about disability may have students who are more willing to disclose about their disability, so they're more likely to have experiences with those students. All we can say here is that there's a relationship, and we can maybe make some predictions on that relationship, but it is far from foolproof. However, one type of predictive design is called an explanatory design. In an explanatory design, you want to propose that the relationship might be causal. You can't determine causality. We can't ever do that with predictive studies, but you can start to eliminate possibilities and test hypotheses as a first step towards building a causal theory that would then eventually be experimentally tested. So if we think back to the science cycle, sometimes it's good to have a step just determining what the different types of relationships are and the relationship between the different relationships. So explanatory studies use the same methods and statistics as other predictive studies, but what they do is specifically set things up so that they can compare relationships. For example, if I split up experience with students with disability into professional experience, students in your classes have had a disability, versus personal experience, a friend or family member has a disability, I can see which one better predicts your attitude towards disability. I still can't say it's a cause, but I can say that one relationship is stronger than the other, or one variable is a better predictor than the other variables. That can start to isolate things that might be causes. So in the future, I can design an experiment to look directly at cause. And that brings us back to our pyramid of designs. So let's go ahead and tackle experimental designs. We'll start this section at the top with true experiments. So as we just mentioned, the goal of true experiments is to determine causality. The most classic example of this in education is an intervention. We want to test whether an intervention that we've designed actually works. Does an intervention work really a cause question, you might be asking? And the answer is yes. What we're really saying when we say an intervention works is we're saying that by doing this intervention, we will cause a certain outcome. The intervention isn't just related to the outcome. We're not just describing the intervention. We're saying that yes, this works. It will cause the change that you are looking to see in students. But not all experiments are looking at interventions either. Some are looking at, for example, causal mechanisms for learning. So as an example of that, I'm working on a study where we compare different ways of structuring a storybook to learn vocabulary. So we want to know whether the structure causes vocabulary learning. Now that's not really an intervention. If it comes out the way we want, then we can maybe suggest to teachers that they look for storybooks with a particular structure. There are practical applications, but it's not a ready-made intervention that can be implemented in classrooms. It's at identifying one causal mechanism of learning vocabulary from storybooks. Now, causality is really hard to demonstrate. Because life and education are so complicated, it's hard to say one thing is a definitive cause of something else. So the methods of experiments are a little complicated. So to understand experiments, let's start at the end. We need something we're trying to affect, a dependent variable, the outcome we're interested in, the change we want to see in the world. We typically measure the dependent variable with surveys or tests or observations. It's exactly the same method as non-experimental studies. Now, you don't see surveys as much in true experiments. They're more common in the non-experimental methods, designs, whereas tests and observations are very common in experimental designs. But in theory, all three can be used here. Then we need the thing that we think might cause the dependent variable, and we call that the independent variable. There she is. I also included a little arrow to show that we think the relationship is causal. But sadly, drawing an arrow isn't the same as doing an experiment, so how do we actually show a cause? Well, there are two big components for independent variables to be a cause. One, it has to come before the dependent variable. So in my vocabulary learning from storybooks example, I couldn't use a book to teach them words like hello, or school, or dinosaur, or princess. Those are words that kids typically know before I ever brought the storybook into it. If I want to test vocabulary learning from a storybook, I have to pick words that kids don't already know. That way I know the storybook is coming before the vocabulary. Before the independent variable comes before the dependent variable. The other main thing you have to worry about when determining cause is that the effect isn't better explained by another variable. So I might think the structure of storybooks is causing the difference, but maybe any kind of book could make that difference, or just reading to kids in general makes the difference, or these particular kids are just unusually quick to pick up vocabulary. Now, this one is a little trickier to solve, this isolating the variable issue. But those of you who remember high school science classes already know what I'm going to say the answer is. That's right. In order to control for every possible other thing that might influence our results, as well as time, this also works great for the time issue, we need to create a group that doesn't get the manipulation, but is in every other way the same. We have one independent variable, but two or more levels of that independent variable. So in my vocabulary example, we need one group to read the book with the structure we're interested in, and one group to read a different kind of book, one that's as similar as possible, but with a different structure. That way we know that the only difference between our two groups is the one thing we're interested in. Then, if we do our study and our statistics and find that there is a difference between those two groups, then we know the difference has to be due to the thing we're interested in. It has to be the structure of the group because there were no other differences between our groups. And if you have an independent variable that breaks down into more than two groups, say an intervention goes for 2 weeks versus 1 week versus no intervention at all, that's fine too. It doesn't have to be two groups. You can have 3 groups. You can have multiple levels of your independent variable. It's just that you have one independent variable. You can also have more than one independent variable, but we'll get into that another time. Now, the obvious question here is, how do we know that there's no difference between our two groups? We don't know everything about everyone, and every person is different. So naturally, there are going to be some differences between treatment and control. So the answer to that is called random assignment. I'll talk a little more about randomness when we get into probability and the actual statistics, but for the purposes of study design, the important thing is that once you have people selected for your study, they have to have an equal chance of ending up in each group. And that means randomly assigning them to the groups using a random number generator or something similar. And the way random assignment works then, just by the properties of randomness, my two groups should end up roughly equal. In fact, randomness is the only way to make things truly equal. Random assignment covers so much, that's why we call it a true experiment. It has an incredible power to make sure our groups are balanced. So all true experiments must have random assignment between groups. If you do not have random assignment, you are not doing an experiment or a true experiment. Okay, so to recap the typical methods for true experiments, they must include random assignment. Hopefully I've made that very clear. They must include random assignment. There has to be some manipulation of the variable, so some people get a treatment or variable of interest and some people don't. And you have to test them on some kind of outcome or dependent variable. And then experiments require inferential statistics. And we'll talk more about the specific ones, t-test, ANOVA, or regression, when we actually talk about stats. And that brings us to our last category, quasi-experiments. Like experiments, the goal of quasi-experiments is to determine causality and test interventions. But as you can probably imagine, there are a lot of situations where random assignment just isn't possible. So that means when we set up our experiment, we can't guarantee that our groups are the same on everything except the independent variable. So we can't truly determine cause here, but we can get some proximal causality. We can test some interventions. We can, get a little close. The methods for quasi-experiments are basically the same as for true experiments, with the important distinction that there's no random assignment. So there's still manipulation and comparing between groups. There's the outcome variables are still measured the same way, so there's still surveys, tests, and observations. And the statistics here are all the same too. What differs is how we get the people into those groups. Probably the most common way that you get people into groups in a quasi-experiment in education is group assignment. So we often want to test interventions at the classroom level. So we assign one classroom to get treatment and one to get control. One gets the intervention and one doesn't. Now, we can't say that the only difference between those groups is the intervention. The teacher is different, or the time of day is different, the chemistry of the class is different. So this has some kind of random assignment because we can randomly assign the classroom, but which kids are in which classroom isn't random. That's determined by somebody else. So it's not a true experiment, but it is a quasi-experiment. A variation of that is called natural assignment, and that's where you want to compare between naturally occurring phenomena. Age differences are the classic example of this. If I want to know vocabulary differences between 4-year-olds and 5-year-olds, I can't randomly assign people to be 4 or 5 years old. They're born when they're born, and you can't really change that. And being 4 versus 5 has a lot of differences between them. So I can't say that vocabulary is due exclusively to age. It might be due to maturity, or language development, or executive function development, or any number of things. So in that case, we can't randomly assign the individuals, but we're also not randomly assigning groups like in the previous example. The group difference is itself the difference we're interested in, so there's no random assignment on any level. Now, we call this natural assignment, but it doesn't have to occur naturally. For example, comparing smokers and non-smokers is considered natural assignment. Obviously, starting smoking or quitting smoking are choices. It's not a natural phenomena like age. So what we really mean when we say natural assignment is assignment that happens outside of the researcher's control. If you're not choosing who is in treatment and who is in control, then that falls under the umbrella of natural assignment. You may have already noticed that quasi-experiments in which you want to find causes but can't quite reach that goal, and explanatory predictive studies where you want to start isolating potential causal variables sound very much alike. And yes, the boundaries here are very mushy and porous. In theory, it's manipulation that makes the difference. It's a quasi-experiment when something is manipulated, and it's exploratory predictive when there's no manipulation. Now, that's really easy with things like group assignment for testing an intervention. One pre-existing group got the intervention, the other didn't. Definitely a quasi-experiment. Similarly, if you're measuring things like whether the relationship between one variable and your dependent variable is stronger than another variable and your dependent variable, that's pretty clearly an explanatory predictive study. But what about when your independent variable is age, as in the example I gave before? Sure, age groups are naturally occurring groups we can compare, but you can't really manipulate age. Let me give you an example. One classic educational psychology study is looking at diagnoses for ADHD between people who were born at the end of the year versus people who were born at the beginning of the year. So if you were born in December 2015 versus January 2016, you're a month or less apart in actual age, but the arbitrary division of December to January is one that is really meaningful when you start school. So kids born in January 2016 are likely to be the oldest in their class, while kids born in December 2015 are the youngest in their class. And researchers routinely find that kids born in December are more likely to be diagnosed with ADHD than kids born in January. So is that a quasi-experiment or an explanatory predictive study? So first question, is there a manipulation? That's the thing that's supposed to make the difference. Well, it's a decision of society to make your school entry dependent on the calendar year that you're born. And the month you're born is really a decision made by your parents, depending on when they, had sex. So the researcher isn't manipulating any of that, at least we hope they're not. But they also didn't pick December and January as arbitrary months. The idea is that this divide might exist because our diagnostic criteria for ADHD may be more about comparing classmates rather than developmental level. So they specifically chose those months because that arbitrary manipulation was there. But they're also not really making a causal argument. They don't think the month that you were born causes ADHD. This is an astrology thing where Sagittarius are more likely to have ADHD than Capricorn. They're just pointing out that if our diagnostic criteria were developmentally calibrated, there shouldn't be this difference in diagnosis based on a month's difference in birth. So there's clearly something else going on, possibly comparison to classmates, but who knows? But that really sounds like they're looking at relationships. They're exploring relationships, which is an explanatory predictive. So it's a gray area. And in education, you find a lot of those because education is really complicated and there are a lot of gray areas. In the end, this is one of those things that doesn't really matter. We don't judge studies based on exactly what design it is. We judge based on whether they're reaching the goals they've set for themselves. If those goals are causal, then neither quasi-experiments nor explanatory predictive studies will get them there. But they both make important points in different ways. So if you're reading a study and you can't quite pinpoint whether it's quasi or explanatory, then that's fine. Don't worry. As long as you can tell what they're doing and why, then you've got a good handle on the design. The exact label is less important. Okay, great. So that's a brief overview of designs based on the purpose of the study. But as I mentioned before, that's not the only way that we can categorize different designs. We're not going to be able to talk about all the ways that we categorize designs, but one of them that I specifically wanted to highlight is the idea of time. All kinds of designs, experimental, quasi-experimental, predictive, and descriptive, all have some time element incorporated. Am I measuring everyone at once? Am I measuring people over a period of time? Am I measuring them once but asking them to reflect back on the past? Those things all influence the design of the study and what conclusions we can draw from the study. So we're going to walk through a couple of the highlights. First, and probably most commonly, we distinguish between within versus between designs. And this difference is really only in the context of experiments and quasi-experiments. So far, when I've been describing true experiments and quasi-experiments, it's been the situation where you have two or more groups that you compare between. That's called a between study. You test everyone at the same time, but compare across groups with different people in each group. But it is also possible to have the same group and have them participate in both the treatment and control conditions, just at different times. For example, if I'm testing an intervention, I can test students before the intervention and after the intervention. So when they've just had regular coursework and then after the treatment. So the same people are tested and you still make comparisons, you just compare the same people at two different times. Time is the variation there. That's called a within subjects design, or sometimes a pretest post-test design, but you can have within subjects designs that aren't necessarily pretest post-test. So pretest post-test is like a subtype of within participants designs. The advantage of a within design is that every person acts as their own control group. So obviously you can't randomly assign here, you're not assigning at all, but you know that your two groups are the same because they're literally the same people in each group. So even though you're not randomly assigning here, we can still draw some causal conclusions because it's the same people. We know our groups are the same. The other advantage is because everyone gets both treatment and control, you don't need as many people to participate as you do if you're splitting them into groups. Now there are some big downsides to that too. For one thing, although they're the same people, they're not tested at the same time. So things that happen between pretest and post-test or between condition 1 and condition 2 could always be a factor. In theory, we want the only thing that happens in that time frame to be our manipulation. But in the real world, that's not always possible. If we have an 8-week intervention, a lot can happen in a kid's life in 8 weeks. Even a 2-day intervention could have different things happen. Additionally, sometimes participating in pretests or the first condition itself can affect the post-test or the second condition. For example, if I have an intervention on nutrition and I start by giving students a pretest, then they get the intervention, then the post-test. The pretest will be part of the learning process for students. So was the learning caused by the intervention, or did merely getting the pretest work as a type of formative assessment that actually impacted their scores at post-test? There's also an issue when you study young people, especially, that they grow and change naturally. So did my language intervention work, or did these kids just get better language skills? Because getting better language skills is something that happens naturally when you're young. So ultimately, whether you're going to use within or between strategy depends a lot on what you're trying to do and how much you think time will be a variable that either helps your study or hurts your study. Now, because of these issues with within designs, some people like to combine a within and between design. We call this a mixed design, but don't get it confused with mixed methods. That's when you combine qual and quant research. This is just combining different designs within quant. So what happens here is that you have a pretest or control condition that everyone gets, followed by the manipulation, which only half the people get. So you can compare treatment and control groups at post-test, but also look at whether there's a difference from pre-test to post-test. This is a little more complicated, but it combines the advantages of comparing groups. There's no time issues here, no order issues, while also having the advantages of within groups. Everyone also acts as their own control. The main disadvantage here is that it costs a lot of money and takes a really long time. You need enough participants to be able to split them into groups, but you also need to test them all at least twice. So this can be a tough one to actually accomplish. This does qualify as a true experiment as long as you are randomly assigning between the treatment and control groups. So you can make causal conclusions based on this. There are some that argue that within experiments can't be true experiments because it doesn't involve random assignment, and some people who think that that's more okay. A lot of it has to do with how much time there is between your first and second testing times, how much time has actually elapsed. But that's, more nuanced of an understanding than we necessarily need now. The important thing to know is that you can mix with and in between to create this kind of mixed design. Another type of time factor is a longitudinal study versus a cross-sectional study. Longitudinal versus cross-sectional designs are actually very similar to within and between designs. Just the scale is sort of increased, and they apply to different kinds of studies, not just experimental designs. Longitudinal studies are when you're testing the same people over time, and cross-sectional is when you're testing everyone at once. The classic longitudinal designs take place over months or years. So for example, if I'm interested in the long-term impacts of bullying, I can send a survey to kids who are victims of bullying in grade 8, and then grade 9, and then grade 10, etc. And then I can connect them all to see what those long-term impacts might be. The classic cross-sectional study is pretty much what we've been discussing thus far. We test everyone at the same time, and we don't, follow them into the future. Inherently, all between subjects designs are cross-sectional because we're only testing everyone once. Sorry, that's my dog flopping her ears. But not all within designs are longitudinal. You could have a within design where, say, students are exposed to one condition and then tested, and then exposed to another condition immediately and then tested. That would still be considered cross-sectional because the testing is in the same session. An example of that would be, say, the implicit attitudes test. If you've ever taken one of those, the idea is it measures your reaction time and says whether you respond more positively to pictures of racial minorities or white faces. It's more complicated than that, but for the purposes of this example, that's what it does. But they're all mixed up. You're getting pictures of racial minorities and pictures of white people all mixed in together. So in that case, it's within subject because you're getting both groups. You are the control and the treatment group. But it's not longitudinal because they're all mixed in together. It's one session. But within subjects designs where, say, you do a pre-test and then a months-long intervention and a post-test, it would probably be considered longitudinal. And of course, the boundary there is porous. There's no determined length of time to call something longitudinal. For education, there are big advantages to longitudinal studies. For one thing, they're the only way we can really track development or learning. Learning requires that you have a permanent change in your knowledge and skills. So you have to be able to measure change specifically, which takes time, which requires longitudinal studies. Similarly, if you're doing exploratory predictive work, longitudinal studies can be essential for identifying which variables come first in the timeline of development. For example, one of the reasons we can say smoking causes cancer is because longitudinal studies are able to show that people start smoking before they get cancer. One big disadvantage of longitudinal studies, though, is that they take time. They take a lot of time. If you're testing students over 2 years or 5 years, that's a big investment. It also makes it very hard to do those kinds of studies for theses or dissertations because you could take the entire span of a master's or PhD just collecting the data. Plus, the longer your study goes on, the more attrition you get. Attrition means people leaving your study. And if you're testing students over years, then some of them will move, some will just get bored and not want to be in the study anymore. So longitudinal studies are great, but they're very difficult to execute in a practical sense. So to get around that issue, what some research do is run tests at one time point, but ask about the past. For example, to go back to our smoking example, another way to look at smoking and cancer is just asking people with cancer, have you ever regularly smoked cigarettes? That would be a cross-sectional study, but retrospective. You're asking participants at one time point, but you're asking them to think about the past. The advantages here are obvious. You can establish a timeline without the time and energy of longitudinal work. But you can also probably already guess the disadvantages. First, retrospective studies only really work if your measure is a survey. You can't really take a test or observation retroactively. Like we talked about with surveys, that relies heavily on perspective. So you're limited by all the ways that surveys are limited. But retrospective surveys also, again, rely on memory, and memory is notoriously unreliable. If you were asked today to answer, say, specific questions about things that happened in high school, you would probably struggle with that. We don't remember our day-to-day high school experiences. So retrospective studies are usually better if you're asking about big events that people are likely to remember, like what year you graduated high school, or long-term things that you don't have to remember specific instances of, like if you've ever smoked regularly, or if you were ever married, or another way they work is if you're asking about the very recent past. And that's probably the most common. You'll ask people to think back to the past week or month. Say a question like, how many days in the past week have you logged on to social media? Importantly, retrospective studies can't be true experiments because, of course, you can't assign anything. You're asking about events that already happened. You could, in theory, have a quasi-experiment, depending on what kind of natural grouping you're looking at, but generally, retrospective studies are in the descriptive and predictive designs. And in case anyone is wondering, yes, we can ask participants about the future as well. That's not its own design, though. We would typically just call that a cross-sectional study where the outcome variable is a prediction or an intention. So, for example, if I was wondering whether motivation in grade 10 would impact post-secondary achievement, I might measure motivation in grade 10 and also ask participants what they plan to do after high school. In that case, I wouldn't call the dependent variable post-secondary achievement. Instead, I call it post-secondary intentions, making it clear that they're reporting their plans, but we do not know if those plans are going to come to fruition. So it would just be a cross-sectional study, but with an intention. We're examining intent. So in that case, we change the dependent variable when we're talking about the future. When we're talking about the past, we don't have to do that. Okay, so those are the highlights of designs. To recap, for our purposes, we're looking at basically two axes, the purpose of the study and the timeline of the study. Purpose is generally the more important for figuring out the big picture of the study design. What kind of study are they doing? What are they aiming for? What are their goals? Whereas time is important for really getting into the nitty-gritty of what they're doing. They're both important when we're evaluating studies, though, so you'll want to make a note of both of them. Okay, and that's it. I'll see y'all next time.